In this video, we are going to assess for goodness of fit of our final model in binary logistic regression analysis in Stata. We have previously looked at how to go through each of steps 1 up to 4, and we shall be interpreting the results of logistic regression in our next episode. So consider liking and subscribing to the channel so that you don't miss out any of our episodes. So before you interpret the results of your binary logistic regression model, what you're considering the final model, which you've obtained through all the steps from 1 up to 4, it is important to check how well does it predict your outcome. And that's what we are calling checking for goodness of fit of your final model. There are 3 different ways that you can use to check for goodness of fit of your final model. One of them is using the Hosmer-Lemeshow test of goodness of fit, which is a statistical test. But you can also look at the classification table of your binary logistic regression model. But you can also look at the receiver operating characteristic, also known as the ROC curve, for your model. So let's start with the Hosmer-Lemeshow test of goodness of fit. This test simply tests the null hypothesis that the model is a good fit. In other words, there is no difference between the observed probabilities based on your data versus the estimated probabilities based on the fitted values for your model. Here is our hypothetical dataset that we want to use to demonstrate this procedure. We have our outcome variable, hypertension, no for those without hypertension, coded 0, and then yes for those with hypertension, they are coded 1. We have 3 independent variables that we want to use to predict whether someone has hypertension or not using binary logistic regression model. So we shall start by fitting our binary logistic regression model before testing for goodness of fit of that model. To fit the binary logistic regression model, simply go to statistics, binary outcomes, and then logistic regression model. In this dialog box, we have to specify our dependent variable, hypertension. Remember, this should be strictly coded as 0 and 1 in binary logistic regression. We also specify our independent variables. We have age, cholesterol, and we have sex, which is a binary categorical variable, which you can specify in Stata by clicking on the 3 dots, and then keep factor variable and main effect, then specify the variable here, sex, add it to the variable list, and then click OK. You can see that we have sex, but with I dot before the variable name. In other words, we are telling Stata that this is a categorical variable. Then click OK. Here is the output for our binary logistic regression analysis in Stata. For now, we are not interested in the interpretation, but instead we want to test for goodness of fit of this model. How good is this model in predicting our outcome? First, we are going to run the Hosmer-Lemeshow goodness of fit test. To run this test, simply go to statistics, post estimation here, and then you select specification, diagnostics, and goodness of fit analysis, then check goodness of fit tests. By default, Stata gives you the Pearson goodness of fit, but we are interested in the Hosmer-Lemeshow goodness of fit, and then we click OK. Here are the results of our Hosmer-Lemeshow goodness of fit test. Our interest is interpreting this p-value. Remember, the null hypothesis is that the model is a good fit. So a non-significant p-value, like we can see here, 0.989, indicates that our model is a good fit. We fail to reject that null. So your model is really doing well in predicting your outcome. The other way you can use to test goodness of fit for a model is to look at the classification table. This classification table simply gives you the sensitivity, specificities, the positive predictive values, the negative predictive values. To get the classification table, simply go to statistics, go down to post estimation, In this dialog box, expand the specification, diagnostic, and goodness of fit. Then you select the classification table with sensitivity and specification results, and then you click OK. In the Stata output, you will have a 2x2 table showing you the true values from your data. If you just run a summary of your outcome variable, you will see that you have 44 people with hypertension and 106 without hypertension. From this table, out of the 44 people who are truly having hypertension from our data, the model has been able to identify only 12. It has misclassified 32. Whereas out of the 106 who do not have hypertension, the model has been able to correctly identify while misclassifying 6. This gives rise to the table we can see down here. By default, in binary logistic regression, it classifies as positive if the predicted probability of having disease is above 0.5. And from our data, true D, what we are seeing here, is defined when hypertension is not equal to 0. In other words, when hypertension is 1, the way we've coded it. In this table, we are presented with the sensitivity and specificity. And when we talk about sensitivity and specificity, we are looking at simply the column totals. So sensitivity is the ability of our model to classify as positive those who are truly positive. So out of the 44 who are truly positive, 12 have been classified as positive. So the sensitivity is 12 out of 44, and we get 27.27 here. You can see that it wasn't doing very well as far as sensitivity is concerned. Then when it comes to specificity, is the ability of our model to classify as negative those who are truly negative. So when we look at out of 106 who are truly negative in our data set, it was able to identify 100. So 100 out of 106, that is the 94.34% that we are getting. So our model was really doing well in identifying those who are negative. For positive predictive value, if a model tells you that 100 people are positive, how many of those are truly positive? So from our results, out of the 18 people who are classified as positive, 12 are truly positive. So 12 out of 18 times 100, it will give us this value of 66.67. Similar thing for the negative predictive value. Out of 132 predicted as negative, only 100 are truly negative to give us this value of 75.76. We also have other values like the false positive rate for the true negatives. Out of our true negatives 106, these were classified as false positives. So 6 out of 106 times 100, it will give us this 5.6%. And the false negative rate for the true positives, out of our true positives, we have a false negative of 32 out of 44 times 100. It is really high here. And when we talk about the false positive rate for classified as positive, out of those the model have told you that they are positive, what is their false positive rate? But overall, the model was able to correctly classify 74.67%. This is a total of these 12 that were classified as positive when they were truly positive, plus the 100 that were negative and were classified as negative. So 112 out of the 150 times 100, we get the overall classification of 74.67%. So by looking at your classification table, you can have an idea of how well or how good your model is performing in terms of sensitivity and specificity, plus these other values such as positive predictive and negative predictive values. Lastly, you can look at the receiver operating characteristic curve for your model, which is simply a graphical representation of the performance of a binary classification model for all the classification thresholds. This ROC curve simply assesses model discrimination, which is an indication of the accuracy of your binary logistic regression model. By discrimination, we mean the ability of the model to distinguish between those who have the outcome, in our case those who have hypertension, and those who do not have our outcome, hypertension. To obtain the ROC curve, simply go to Statistics, Post Estimation, and then under Specifications, you're going to see here ROC curve and area under the ROC curve. So we are going to ask for computing area and graph curve for all the observations, and we click OK. Here is our ROC curve, which is a plot of sensitivity over 1 minus specificity. Generally, values of the area under the curve of 0.7 and above are considered the acceptable discrimination. Your model is able to discriminate between those who have the outcome and those without the outcome with a considerably high level of precision. So your model is a good fit. Those are the 3 different ways we can check for goodness of fit of our logistic regression model. If you found this video useful, consider liking and subscribing to the channel so that you don't miss out any of our episodes. Next, we shall look at how to interpret results of our binary logistic regression in Stata. See you in the next episode.